are back. And we are back at Coco Talk Live. And we've got a very popular segment, especially for all the millennials. All the young kids these days are really saying, you know what? If only I could learn a 30-year-old language that lets me communicate with a 40-year-old processor in an efficient way, I could Snapchat the hell out of that, right? So that brings us to assembly language with Steve Bjork, who is very graciously sharing with us his knowledge and wisdom on this subject, and he's presented us with prepared another presentation. Blah, blah, blah. I can't talk. All right. But how about we do this? Let's see if my music is working, because Curtis Boyle's giving me all kinds of little cool sound clips. So let's try one of these here at random. Whoa. Let's get our assembly going, people.
Okay, well, this week we're moving along more with the 6809 command set, the instructions that are inside the processor. And we're going to take a look mostly at the ones that do arithmetic, math work, and like that. But first, we're going to kind of do a little bit of recap by looking at storage. See, most instructions either move information into the CPU, move it out, or manipulate it in some way. And so we're going to look at loading and storing, moving the basic instructions for moving information around inside the computer, and then doing a little math. And then we'll get into some of the other ones. So go to the next slide there, Steve. All right. We're going to take a look at loads data, saves data, and math. Later, we're going to talk about logical operations, branching, and system operation, commands that kind of affect the status of the CPU. So why don't we go to that next slide? We're going to take a look at load. We kind of talked about this one last week before with basically you can move information into the CPU by moving into any of the registers. Your registers are A and B, which are 8-bit. Then you have D, X, Y, S, and U, which are 16-bit. That's why they call this an 8/16-bit CPU. The first CPUs, like the 6800 and the good old 6502, those are strictly pretty much 8-bit CPUs. Their mathematical operations were only 8-bit. Now, there's another thing that's whenever you're doing work such as loading and saving and arithmetic, you're going to affect the condition code registers. And these are special registers that let you know things like, was the number 0 that you just loaded? Or was it a negative number, which we'll talk more about later? But basically, it sets some of the registers. So like, for example, up at the top, we've got load A with FF02. What that does, loads the A register, which is an 8-bit register, with the information that's stored at FF02, which happens to be an I/O port on one of the PIAs. And of course, that's 8 bits. Now, when you load up A and B, those are only 8-bit operations. And as I said earlier, the D, X, Y, S, and U are 16-bit registers, and you only load up 16-bit. Now, I noticed in Discord, there was somebody trying to play around with, they didn't quite understand why they couldn't load up just the upper part or the lower part into a 16-bit register. But you just got to remember that there's 8-bit modes, 16-bit modes, and the twain shall never meet. You have to do one or the other. In any case, let's go to the next slide. Just like you had load, you got store. You can take the information that's inside the CPU in the registers and store it into a memory location. And in case like store A at FF02 means take the information that's stored in the A register and put it at memory location, which happens to be an I/O port of FF02. It's an 8-bit operation when you use the A and B registers, and 16-bit when you use the D, X, Y, S, and U registers. Also, the condition code register is affected on the 0 and negative flags. These are flags that are useful for figuring out what's going on in doing branch operations. Let's go to the next slide. Well, lots of times, and you've seen this with your own basic programming, you basically just want to load a 0, or you want to work with a 0. Well, they actually give you a command so that you can clear either the A register or the B register to 0, or you can clear a memory location. This is only 8-bit operation on the 6809. There's no 16-bit clears.
Okay.
So it does affect the, it sets the 0 flag after the instruction's done. So you know that the last operation came up with the 0, obviously, since you just basically loaded A with 0 or loaded a memory location with 0. And then the negative flag is cleared, because obviously a negative number, 0 is not a negative number. But basically, that's one thing that they found that programmers use a lot, is they clear things. They set them to 0. So they made this a special case instruction. But once again, on the 6809, this is strictly an 8-bit only operation. It does not work on the D, X, Y, U, and S registers. Okay, let's move to the next slide. We're going to get into math. The math on this particular CPU is fairly simple. We can add and subtract numbers. There is a multiply command, but we'll talk about that next week. Anyways, first one up is a simple add. Add allows you to add a number to either the A, B, or D registers. So A and B would be 8-bit operations. The D register is a 16-bit operation. In the example that I show you of add A, number 3 means take the number 3 and add it to the A register. It's only an 8-bit operation. The next example I give you after that one is add D to, from add 03 to D. D, as you recall, was the 16-bit register of A and B put together. Mm-hmm. And it goes to memory locations 03 and 04, with 03 being the high part of it, being like the A part of the add, and the 04, the byte after it, that's the low part, basically gets added to the B register. So it's a fast way to do a add of A and B together. It does 16-bit. Now, these are the only possibilities of doing something with the add command. They're the only registers you can add to. There is some tricks you can do with the other index registers, but we'll be talking about that sometime later. The carry flag, which basically means that if you added two numbers together, let's say we're doing an 8-bit add, and we add the number, let's say 200 plus the number 200 together, you're not going to get 400. What'll happen is you're going to get a carry plus what the remainder would be. See, the thing is, when you only got 8 bits, 8-bit stops at 255. 256 is basically would be carry plus a 0 because you rolled over. So the carry flag will be set. There's a thing called a half carry. That's somewhere in the middle of the byte. If you had, let's say, 10 plus 10 together, you get 20, but that's really halfway through the byte you're adding a carry. Not half carries don't get used too much. Then you also have the 0 flag being affected. It means that if you've done this addition and your product is 0, then the 0 flag is set. There's also a negative flag if you're working with signed numbers, and we're going to be talking about signed numbers later on. We're just really talking about strictly integer numbers at this time. And then the overflow is used for if you have a signed number overflow. And all those flags are affected. And these flags are very important because lots of times you'll do some operation and then you'll branch to another part of your program based on the condition of these flags, such as if you had the overflow, that could be an error condition. So if basically you're doing integer numbers, you're adding together, and you get a carry, ooh, we just had a problem. Let's branch to a routine that's going to handle the fact that the number got too big. So,
yeah, the flags are kind of like, if trying to put it into basic terms, it's kind of like part of the if-then. The flags are used to figure out if a certain thing has happened, then do this, and that's the carry or the condition code combined with a branch based on the condition codes.
Like in basic, if you do a divide by 0, you get an error because you can't divide anything by 0. It creates an imaginary number. Well, basically creates that error for you and stops the program because you're doing something illegal. Well, you have to, in assembly language, figure out what is illegal and make sure that you take care of it. See, it's little things like that that does make assembly language program a little harder, because that's where bugs can creep in and you get weird things that happen. So these flags are going to be very important and like that. Let's go to the next one. Next slide. Now, before, as we said, you might add something together and you're going to get a carry because the number became greater. Well, they don't want to leave you out in alerts. They came up with add with carry. This means you could add two numbers together, and then the next thing you do is another add for the bytes that you're adding up, and you can have the carry from the last add affect what you're doing. So it's basically looking to see, oh, did the carry flag get set? Add one more. And you have add with carry only working on the A register and the B register. It does not work with the D register in the 1609 instruction set.
Yeah, and this is just like old-fashioned adding at school with math. If you were adding like 9 plus 4, it doesn't fit into the single digit. So you get a carry. You do 9 plus 4, and you put 3, and the carry, you put that little 1 over top of the second digit, and you add that.
Yeah.
You get 13, and that's exactly how this works here.
Okay.
Definitely. It's a way to handle larger and larger numbers and make sure everything carries across, literally. And it's another important thing, which we will do examples of how you use it. So you're not left out in the lurch when you're adding up large numbers together. This will allow you to do the carry.
Yeah, and I just want to point out too, like some people might assume that this is used to say add D, right? Like you're adding B and then you're carrying into A. You can actually go with memory locations and make this number as big as you want. If you want to get, a number that's 5,000 digits long, you can keep going through adding from the lowest to the highest with the carry, and you'll actually get the accurate result after the whole add's done.
See, in some of my video games that I create, the position information is 3 bytes long. Well, I can use the add D to do 2 bytes worth of information, but then I've got to use this add with carry to get that extra byte that I need for the computations. So it's very useful. But you only have add with carry on the A register and the B register. So if you're doing memory locations that you're trying to add up, you have to load up the A register or B register with the number, and then you could do an add with carry and like that. By the way, if we go back a couple of slides, one more and one more, back to the load. Notice that I stayed down at the bottom of this slide that the 0 flag and the negative flags are set when you load a number, but the carry flag is not affected. They were thinking ahead when they were making this CPU that they didn't want to change the carry flag from a numeric operation during a load. So you can sit there and load up information and have the carry flag not change on you. So when you do the add with carry, it works correctly. We'll go over exactly how that's used later in our math examples, but it's just one of the forward-thinking things that they're thinking about in designing the CPU to make programming easier for us. Let's go back to that slide. Yeah, add with carry. One more. And, well, we've got the add instruction. Well, it would be very helpful if we could subtract numbers too. Let's go to the next slide. Subtract works just like the add. You can add, or you can subtract numbers on the A, B, and D registers, just like you do the add. And the example I have here, subtract A with the number 3, subtracts the number 3 from the A register. You can also do a 16-bit by using the subtract D. And the example, it'll subtract from the D register that's inside the CPU with information that's stored at memory, in this example, memory locations 03 and 04. And of course, all the flags are affected. So you kind of know if you've had, if you subtract a larger number from a smaller number, you want to know that you've had a problem. And the flags will tell you. Let's go to the next one.
Let me ask you a quick dumb question here, because I'm trying to understand right now. When you talk about subtracting from the D register, so we have 16 bits. We're subtracting 3 from a 16-bit number, and you're saying it's applying to 2 8-bit locations. But wouldn't the 3 only get subtracted from the lower order bits and not both? Or
no, this is an extended addressing. Like you notice the number sign on the sub A, that means we're subtracting the literal number 3. That means basically A equals A minus 3. The sub D is using just the $, which means extended addressing, which means we're telling to subtract from a memory address whatever's stored in those memory addresses. So the memory address 3 is where you're getting a 16-bit number to subtract from D. It's not the literal number 3.
Okay.
Is that clear?
A little clearer, sure.
Yeah, we talked about that in the last lesson about the #3.
Oh, that's right. Yeah, pound is the decimal.
Yeah. Pound, well, no. Pound means immediate. The information of that we're subtracting is actually inside the instruction. It says, take this number that you see here and subtract it. Where the $3 says, this is the memory location that holds the number we're going to subtract from D.
Oh, so whatever's stored in D, we're saying subtract the value of location 3 from register D.
Right. It's actually locations 3 and 4.
3 and 4 because it's 2 bytes for that whole register.
It's 16-bit.
Yep.
So
now, if we had said subtract A, $3, it would only take what's held in memory location 03 and subtract it from A. It's just that because we are using D,
right. Okay.
We're
right.
having
So this is 16-bit subtraction from a 16-bit number. So you have to specify. You're assuming 2 locations.
Exactly.
Okay.
Yeah.
I'm caught up now. All right. Sorry.
Yeah.
No, that's good.
Well, you didn't
read
read
the kind of questions we want.
Steve, you got to sit there and look at last week's lesson before you go through this one.
I was there.
Well, he had his brain meltdown from getting too technical recently, so he kind of
Yeah.
lost some memory there.
Okay. The next up is kind of like what we had with add with carry. We got subtract from carry. And it's pretty much the same thing. If the carry flag is set, it subtracts 1 more so that we can basically handle something larger numbers, multiple numbers, as we talked about before with the add with carry.
Yeah. Sometimes this is referred to as subtract with borrow too, which is, I guess, the math term, but it's the same thing.
Exactly. And next slide. Well, remember before earlier, one of the popular things to do was basically get a 0 into a register or a 0 memory location. Well, adding 1 and subtracting 1 are very common operations. So they make a special case called ink. This adds one to a register and memory location. You can add one to registers A or B or to a memory location. This is only an 8-bit operation, 1 byte only operation. In
So
the case
ink would mean increment.
exactly. Yep. So ink A adds 1 to the A register. Now, if the A register's got the decimal number 255 in it, you ink it, it becomes 0 because it loops around. And let's see, you can also ink a memory location. So like ink $3 will ink the memory location at 3. Now, only the 0 and negative and overflow flags are affected. The carry flag and the half carry flag are not. This is so that carry information could carry over from a previous add. So that's the one thing you gotta be tricky for. And usually most of the time programmers only care if the number is negative 0 after this type of operation. But it's used for mostly counting.
Okay.
Like a for next.
Like a for next loop. Yeah.
Right.
And if we go to the next one, is decrement. And believe it or not, most assembly language programmers use this more than any other instruction because we like to count down. And the reason why we like to count down, let's say we want to do something 10 times. We load up the location with the number 10. When we use the decrement, guess what happens when we decrement 10 times? We end up with the number 0, which is makes it very easy to test whether or not we should loop.
Okay.
Just test the 0 flag.
If not equal to 0, then continue to decrement.
You got it. It's probably used more than any other instruction practically in doing coding of assembly. So, but it works just like increment, except for it subtracts by 1. And that's pretty much it for this week. I wanted to keep the lesson short because wasn't sure how much discussion.
It's a lot to absorb if you've never done this stuff before. So
Right.
It's nice to do it in small chunks.
Now, somebody was asking me earlier on Discord what book I was basing my lesson on, and I chose not to base it on any particular book. This is based on my knowledge and of the instruction set like that. Plus, I've taught it before. But the key here is that we're going to go through and we're going to have little segments like this, bite-sized stuff. But you're more than welcome to download anything that's out there on the 6809 instruction set. Just do a Google search on that term, 6809 instruction set, and you're going to find the instructions. And each week we will continue to go through and fill it in. Now, we have a couple of special case instructions that we're going to talk about that are still in the math category, such as sex.
Multiply and sign extend, yeah.
Yep, sign extend. So we'll go with those next week, and then we'll get into the logical operations. That's where you're manipulating bits around, which are very handy for graphics. And
Very cool.
We'll just keep moving on with that.
Yeah, I like it.
And we do encourage people, if they have questions, between the day of the episode's aired and the next week before the next one, if they have any questions or need clarification, anything that we discuss on this, that please send us an email or comment on YouTube or whatever, and we'll bring it up before the lesson and help clear things up if it's not totally clear to some people.
Right. You can do that in Discord if you're on the Discord server, which there should be a link to that in here. If not, I can put that for you. The other thing you can do is you can leave a comment on the video. So when you're watching this video in a replay, you can just leave a comment, and we'll get to that. Or you can send an email to cocotalk@cocotalk.live, and we'll get it that way.
Yeah, I'm also looking at trying to schedule maybe something like on Tuesday evenings at 9 o'clock Eastern, 6 o'clock Pacific, where we can just do some sort of assembly talk or something like that.
Okay, in Discord?
In Discord.
Okay.
And actually, I just wanted to mention too, my favorite book for actually learning assembly was Lance Leventhal's. That book was the one that taught me the most, aside from Steve himself, back in the day. So that's a good book to actually get into, is the Lance Leventhal 6809 series.
Good. Those, do you know if those are on the Color Computer Archive by any chance?
Yeah, it's on the Color Computer Archive.
Okay. Now, it wasn't, because I think the Coco crew had interviewed him. He had two different series, right? He had one that was like explaining all the instructions, and there was another one that was kind of like a reference set. Like, well, if I want to achieve this, what's the command I use to do that? So wasn't there two books he had on that? And I forgot the distinctions in the titles.
There was two different covers of the same book that I remember. I don't know. Was there a second copy, Curtis?
Yeah.
I don't remember a second book by Lance on the 6809.
Maybe it was a different author, but there was somebody who had all these processor books where he wrote all the books, and he had one book that basically just explained everything, and then the other one was more like a reference guide where
X?
I don't know. I'll have to go back and check on that. So was that Atkinson? So Ed Snyder says check out Darren Atkinson's instruction set reference for the different ones for the 680 and 6009s.
Yeah, he's got the 639 stuff in there too, and tells you which ones are unique to each. Yeah.
What's Mark got going on here? Which book is that, Mark?
Leventhal.
I'm having a hard time figuring how to freaking click on one person now with this new software. I thought I had that down before. If I click on Mark one time.
Got the Lance Leventhal one up.
Yeah, that's the one I got.
Lance Leventhal. Okay.
Yeah. I think I've got that somewhere in my collection. Actually, when I was learning 6809, I just had some reference material from Mole Roll, and that was it.
Yeah, that little thin 8.5 by 11 or whatever it was.
Oh, it was a card that just kind of folded. That was like maybe 3 inches across by about
reference card printed with blue or purple, depending on which processor.
Actually, mine was green because it was.
Were these done on a Ditto machine?
And there were some other good books too. I mean, Lawrence Teppel did some stuff that was Coco specific, as did William Barton Jr. There was also Rodney Zacks did a generic 6809 book too, which is pretty good. There's quite a few references here. Just search on the web, you'll find them.
Well, see,
the Barton books were one of my favorites too.
See, before I learned 6809, I had 6850 under my belt, 6800, 8080, Z80, and there was an RCA chip, 18 something or other.
Wow.
1802 or something?
I had all these different chips, but as I'm going through the thing and I'm looking at the way everything's laid out, instructions, I go, this can't be this simple. Because it was like 8080. Every time you tried to do something, there was an exception. No, you can't do it that way because you're using these registers. No, you have to do it this way. And it's ridiculous. And with the 6009, it was like, okay, I want to do something. It was like there was 5 different ways to do it. It was just figuring out which way was the best way.
All right.
With all these machines
really at that time fell in love with the 6809.
Do you ever get confused with all these instructions in your head?
Well, when I was working on developing the DVD system, I did get a little confused on that, but it was all the different ways they wanted to do things on that. That was a fun project, but not now. 6809, I stayed very, very clear on that.
Yeah.
And the only other processor I liked almost as much was the 68,000.
8,000. Yeah.
Okay, how about we do this real quick? Lessons learned from the past. We've just finished the presentation. Let's take a brief commercial break, and then we'll come back for the follow-up questions and answers from the panel and from the audience. And that way it doesn't become a super-duper long segment. But so far, I'm with you. I'm following you. I appreciate it. And I'm happy. So it's good, right? So
No rage quit today?
No rage quitting today. So we're going to take a brief commercial break, give everybody a chance to go potty, do whatever you got to do, and we'll come back, and then we'll have questions from the panel and feedback from the viewers on what we just learned in this week's assembly. So we'll be right back. Thanks, everybody. So that's one of the things that we'll hopefully talk about today. And by the way, we've been joined by Grant Leedy. Is Grant still here? Grant was here for a minute, and then he's gone. Okay, hopefully Grant will come back, and then Richard Lorbieski had to leave, and so I'm glad Richard was able to join us. He did say goodbye in the chat. Okay, very, very cool. All right, so we're back. We just finished the segment in assembly, and so now is the time for, I guess, the people in the panel maybe to chime in on what they thought of it, anything you wanted to ask or contribute or add to that, and we'll ask people in the audience too. Hey, Grant Leedy is back. Welcome back, Grant Leedy. Grant, do you copy? Earth to Grant. Major Tom to ground control. Okay. Grant.
Yes, I'm here.
There you go. Hey, welcome to the program, Grant Leedy.
Sorry, I had a little computer problems here today.
No problem. All right, so what Peanut Gallery, what do you guys have to say about our latest assembly segment? Anyone?
What was the topic for today?
Well, hopefully it wasn't too long.
No, it was good. It was a good length. I like how the brevity of it was nice.
Do you have anything you want to add to it, Grant, or add with Carrie?
No, unfortunately, I missed part of it, so I will have to rewatch it here later. So
okay,
Yes.
Paul Fiscarelli just gave us a thumbs up in the live chat. So thumbs up, great content. Yeah.
Oh, the only thing that I should really add is on the increment and decrement commands, it actually does set overflow when it reaches 0 or 255.
Okay.
All right.
And explain that in English.
That's where Steve was talking about that condition code register. It has an overflow bit.
Uh-huh.
And if you actually hit 256, it actually will set the overflow bit as well as 0.
Okay.
I should mention too, I mean, one thing Steve's mentioned that the 6-9, one of its beauties is that there's so many different ways to do things, unlimited. I mean, you could do an add A1, which is the same as an inc, as far as adding 1 to it. The condition codes are a little bit different because it does more signed math and stuff, but basically you can do the same thing. But the advantage of increment or decrement, if it's the type of instruction you want to use with the condition codes you want to check for, is that it's actually a byte smaller. So actually will shrink your code compared to, say, doing a sub A number 1 or add A number 1 or something.
Very cool. Very, very cool. So, yeah, we just saw a commercial for Radio Shack TV computer games, and I think that's one of our little news items that we'll get to in a little bit today is, the fact that Radio Shack is you cut the tail off the lizard, and sometimes it grows back. So Radio Shack is reviving itself in some form.
Steve, I just want to say one thing to Bill's comment.
Hold on. I need to
my
mute.
slide for increment and decrement, I do state that the overflow flag is affected.
Okay, it's in the slide. All right.
It's in the slide.
I had to mute Bill. I'm hearing a lot of background noise from Bill. So, Bill, I am going to unmute you, but you just know that you're generating some noise for us. So, yeah, that was in your slide. Okay, that's cool. Paul Fiscarelli said good. Now, these are good segments. And what I need to do too is, here's my challenge. This is what I noticed too when I listen to the podcast and stuff, is that Bill, you're killing me. Are you outside? No, you're muted now. Who else is outside? Maybe that's Jason. Okay, somebody's killing me with the wind there. So when I'm here on the show and I'm trying to absorb everything that's being said, there's only so much I can absorb when I'm hearing it live, because there's just so much distraction between background noise and the live chat, and there's this and there's that and the other. I just feel like I can never fully appreciate everything that happens while it's happening. And so one of the nice things is that when I make the podcast version and I listen to that in the car, because I'm listening for all of these things like background noise and things like that. So I'm trying to do some quality control. I actually pick up on a lot of things that I didn't fully digest the first time around. And so I've noticed that on a normal show, and I noticed that a lot even on the After Dark shows when I was kind of proofing some of those, that there's so many things that get said, and some of the stuff that we say, we're saying it so quickly, and people are sometimes talking over each other. Sometimes there's these little quips or these little comments and little funny remarks, and so many things happen. It's really hard to kind of process it all in real time. And I guess that's one of the benefits of being able to, have these replay options and things like that. So I appreciate these segments, and I know they're gonna help a lot more people over time, things like that. Anybody else that wanted to add on to the assembly talk before we move on?
Don't think so.
Okay. This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Coco Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Differendaffer for making my head explode. Please help support the Coco community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Coco Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.